Today I will talk about geodesics. In order to do this, it is necessary to recall the notion of flow and the fundamental theorem on flows. So let's start. Suppose that X is a smooth vector field on a manifold M, then a smooth curve gamma defined on an interval I with values on M is an integral curve of X if gamma prime t equal X at gamma t. So this means that X restricted at gamma t, evaluated at gamma t, is the velocity vector of gamma. A fundamental fact about vector fields is that there exists a unique maximal integral curve starting at each point, varying smoothly as the point varies. The collection of these integral curves is called a flow. I will provide you with a rigorous definition in a few minutes. I will start writing down the definition of flow domain. So if M is a smooth manifold, flow domain for M is an open subset D containing R times M such that for each P in M, the set dP defined this way, T in R, such that Tp belongs to D, is an open interval containing 0. Then, given a flow domain D, so given D and a map theta on D with values in M, for each T in R, we define MT as the set of points in M such that Tp belongs to D. And theta t defined on MT with values in M theta p from dp in M, writing theta t p equal theta p t equal theta tp. So a flow on M is a continuous map theta from D into M, where D is a flow domain such that theta 0 is identity theta t composed with theta s at p is theta t plus s at p, wherever both sides are defined. So if theta is a smooth flow, then we can compute theta p prime at 0. This is a vector, of course. Which defines a vector field X called infinitesimal generator of theta. And now I want to present, as announced before, the fundamental theorem on flows, which says that if X is a smooth vector field, on a smooth manifold, which is supposed to be without boundary, then there exists a unique smooth maximal flow theta from D into M, whose infinitesimal generator is X. The flow satisfies the following properties. 1. For each P in M, theta P from dP into M is a curve. It was not clear from the definition. This is a curve which has the property to be the unique maximal integral curve of X starting at P. 2. If S belongs to dP, then d theta S P is equal to d P minus S, that is T minus S, such that T belongs to dP. This statement says that if S belongs to the interval of definition of the unique maximal integral curve starting at P, what is the interval of definition for the unique maximal integral curve of X starting at theta SP? Simple. It is given by a translation by S of dP. And part number 3, for each t in R, mt, I defined this set before. Maybe let's write it again. P in M such that Tp belongs to D. That one is a set which is open in M, and theta t from mt to m minus t is a diffeomorphism It is possible also to write down the inverse. It is given by theta minus t. And I want to recall a lemma known as escape lemma, because I will use it in the proof of a theorem. So suppose that M is a smooth manifold and X is a smooth vector field. Then if gamma is a maximal integral curve of X, whose domain I has a finite least upper bound B, then for every t0 in I, gamma of t0 b, the image of this interval is not contained in any compact subset of M. Okay, now we are ready to talk about geodesics. So suppose that nabla is a connection in the tangent bundle Tm, then for every smooth curve gamma, the acceleration of gamma is the vector field given by dt gamma prime along gamma. So I want to say a word about this definition. We don't define the acceleration to a curve to be gamma second. Why? Because if gamma is a curve on a manifold M, it does not make sense to compute gamma second as a limit, let's say at t0, limit as h tends to 0 of gamma prime t0 plus h minus gamma prime t0. And the reason why this is not the good definition is that gamma prime t0 plus h and gamma prime t0 belong to different tangent spaces, so it doesn't make sense to write down gamma prime t0 plus h minus gamma prime t0. And this is the reason why connections has been introduced, and this is why we use this covariant derivative along the curve gamma for defining the acceleration. And now I can give the definition of geodesic. A smooth curve is a geodesic with respect to the connection nabla if the acceleration is equal to 0. I want to recall a formula suppose that V is a vector field along gamma suppose that x1, x2, xn are smooth coordinates in a neighborhood of gamma t0, then we can write Vt as Vjt delta j at gamma t, where these are functions defined in a neighborhood of t0. Then if we use the theorem which describes the property of dt, the covariant derivative along gamma, and the fact that dj is extendable, then we have that dt vt is given by v dot j t dj at gamma t plus vj t nabla gamma prime dj at gamma t. And now we can expand this term, and after a change of index in the first summand, I mean I will use k instead of j, I will get that this is equal to v dot k t plus gamma dot I t bj t gamma I j k along gamma t. Why we recall this formula? The reason is that if gamma t can be written as gamma 1t, gamma 2t, gamma nt in coordinates, then the condition dt gamma prime identical equal to 0 translates to gamma dot dot k t plus gamma dot I t gamma dot j t gamma I j k at gamma t equal to 0. So I got this formula using this formula here, where Vt is being replaced by gamma prime t. And I made a change of notation. I used the dot symbol when I derive a component function with respect to the variable t. So this is a system of second order ordinary differential equations where the unknowns are the functions gamma 1, gamma 2, gamma n, And as any system of ODE, we want to solve it. And now it's the good moment for presenting the theorem about existence and uniqueness of geodesics. So as before, M will be a smooth manifold without boundary, and gamma will be, nabla will be a connection in the tangent bundle M. Then for every P in M, W in TPM and T0 in R, there exists an open interval I such that T0 belongs to I and a geodesic gamma on M such that unfortunately I have to erase such that gamma at T0 is P, gamma prime at T0 is W, and any two such geodesics agree on their common domain. Let's try to prove this theorem. So suppose that x1, x2, xn are smooth coordinates on U, where U is an open neighborhood of P. So a smooth curve in U can be written as gamma 1t, gamma 2t, gamma nt. This is a geodesic if the system of ODE that I erased is satisfied. And now we use, okay, maybe let's write down the system again. So this is a geodesic if gamma dot dot kt plus gamma dot I t gamma dot j t gamma I j k gamma t, this is 0. Now we introduce some auxiliary variables. The reason is that this is a system of ordinary differential equations of order 2. We want to construct a system equivalent to this one of equations of order 1 and apply the theorem of existence and uniqueness of solutions for such a system of equations. So we call Vi gamma dot I, and this means that we get the equations gamma dot kt equal vk t, v dot k t, this is minus vi t, vj t gamma I j k gamma t. So now we can use x1, x2, xn, v1, vn as coordinates on u times Rn, and this system here this is the collection of equations for the flow of G in key of u times Rn given by this vector field G equal vk d dxk at xa minus vi vj gamma I j k at x at xa. Now we use the fundamental theorem on flows, and we get that for each PW in U times Rn and T0 in R. There exists an open interval that I will call I0 with T0 in I0 and a unique smooth solution zeta. No, this looks similar to Xi. Zeta to this system such that zeta at T0 is a PW. You can check that if you write down zeta t as gamma I t vi t, then gamma t given by gamma 1 t, gamma 2 t, gamma n t, that is the map that you get considering just the first n components. This is a geodesic satisfying gamma t0 equal p, gamma prime t0 equal w. So we were able to prove that such a kind of geodesic exists. Now we have to prove the uniqueness part. So suppose that there exists gamma tilde from I into M such that gamma T0 is equal to gamma tilde T0 and gamma prime T0 is equal to gamma tilde prime T0. We can define zeta and zeta tilde from T0 minus epsilon, T0 plus epsilon with values in U times Rn, exactly as before. And these two maps satisfies the system I raised the one with gamma dot kt equal vkt, v dot kt equal minus vit, vjt, gamma ijk gamma t. Then you can use the theorem of uniqueness for the solution of a system of ordinary differential equations, and then you have that zeta and zeta tilde agree on an interval of this form. So far we proved only that gamma, gamma tilde coincide on an open set, an open interval, this form here. We want to prove that they coincide on I. So suppose by contradiction suppose that gamma b different from gamma tilde b with b in I. We can suppose that b is larger than t0. The argument for handling the case b smaller than t0 is similar. Define beta as the infimum of beta in I, such that b larger than t0 and gamma b different from gamma tilde b. So if you want to make a picture, suppose that this is gamma t0, which is also equal to gamma tilde t0. This will be gamma beta, and this is the infimum of the values of the parameter t in I, such that you have this inequality. Now we can use the fact that gamma, gamma tilde are smooth, in particular continuous, to say that gamma beta coincide with gamma tilde beta. So I can write here also gamma tilde beta. And gamma prime beta equal gamma tilde beta prime beta. This follows from the continuity of gamma prime. Then I use again the uniqueness of the solution of a system of ODE to say that gamma equal gamma tilde in a neighborhood of beta. So this means that beta is not the infimum of this set here, because what we are saying here is that if this is gamma beta, which coincide with gamma tilde, I'm saying that gamma and gamma tilde coincide on for values of t larger than beta. So they coincide on an open neighborhood of gamma beta. So we got a contradiction, and this implies that gamma coincides with gamma tilde on I. This is the end of the proof. Now we are ready to talk about maximal geodesics. So geodesic on M is maximal if it cannot be extended to a geodesic on a larger interval. In other terms, it does not exist gamma tilde defined on I tilde which is an interval containing I properly, such that gamma tilde restricted to I is gamma. Geodesic segment is a geodesic defined on a compact interval corollary of the theorem I proved a few instants ago is the following. For each p in M, and V in TPM, there exists a unique maximal geodesic gamma in M such that gamma 0 is P, gamma prime 0 is V, defined on I with 0 in I. How to prove this corollary? Define I to be the union of all intervals containing 0 and such that there is a geodesic let's say Ij, gamma j, Ij with values in M, such that satisfying gamma j 0 equal P, gamma j prime 0 equal V. The theorem we proved implies that gamma j coincide with gamma I different from j, where gamma I, gamma j overlap. So you can define gamma on I taking the common values of these geodesics. And it is clearly the unique maximal geodesic having this property. The unique maximal geodesic gamma such that gamma 0 equal P, gamma prime 0 equal V. This is denoted by gamma V, and is called, maybe it's not necessary to write, it is called the geodesic with initial point P and initial velocity vector V. In this textbook, the initial point does not appear in the notation used for the maximal geodesic because you can recover the initial point P just taking the projection of V, where pi is a projection from Tm to M. Now let's change topic, but not that much, because we will talk about parallel transport because I say that we don't change too much topic, because the parallel transport is a construction involving covariant differentiation along curves, as we did for geodesics. We will suppose that the manifold we consider have no boundary, and nabla is a connection in Tm. So we say that smooth vector field V along a curve gamma, which is supposed to be smooth for the moment, is parallel along gamma if dtv identically 0. This definition has a consequence, which is immediate, and it involves geodesics. A curve is a geodesic if gamma prime is parallel. So this is just a reformulation of the definition of geodesic. Nothing special, but it is worthy to mention. So suppose that the representation in local coordinates of gamma is this. Then V in T gamma is parallel along gamma if and only if V dot kt equal minus V j t gamma dot I t gamma I j k at gamma t, where what is Vj? they are the component functions of Vt with respect to the frame dj. Once again, we got a system of ODE. So this means that there exists a theorem of existence and uniqueness for this system. The difference with previous system is that this is linear. Why? Because the unknown here are the component functions Vj. Here you have that the derivative of Vk is a linear function involving Vj. So this means that we can prove a better result compared to the result involving the geodesics. So we have this theorem, existence, uniqueness, and now we have also smoothness. Of the solution. So let I be an open interval and for j and k satisfying this chain of inequality, let ajk be smooth functions defined on the interval I. For all t0 in I, and for any vector C1, C2, Cn in R, the linear initial value problem v dot k equal akj vjt, vk at t0 equal ck has a unique smooth solution on all of I. So this is a result similar to the corresponding result involving the geodesic. The novelty is that the solution depends smoothly on Tc in I times Rn, where C denotes this vector here. C equal C1, C2, Cn. It is clear that this is the theorem we need, because the equation, the system of equations, which is equivalent to dTV identically equal to 0, has this form. I don't prove this theorem. I will try to make a summary, a sketch of the proof. So the first step is assume T0 equals 0. Otherwise, replace V k t by V k t minus T0 and A k j t by A k j t minus T0. Then the first step is to prove that there exists one, show that there exists a one-to-one correspondence between solutions to the equation star and integral curves of the auxiliary, the vector field y equal ddx 0 plus a1j x 0 x j ddx 1 plus ajn at x 0 x j ddx n, where x 0 x1, xn are coordinates, standard coordinates of I times Rn. Then you use the fundamental theorem on flows. This implies that for each C1, C2, Cn, there exists a maximal integral curve eta of y, satisfying eta 0 equal 0, C1, C2, Cn. So what we are doing here is that since we want to prove that the solution to the equation d to the system dt v equal to 0 is smooth with respect to C1, C2, Cn, we constructed this special vector field, and we proved that there exists a maximal integral curve satisfying this initial condition and which is smooth also with respect to these arguments, which now are considered as a parameter of the curve. Sorry, parameters of the solution. So this solution exists, so defined and defined on I0 contained in I. Step number 3. Show that I0 is equal to I. So this is the structure of the proof. And let me check how much time I have. I think we could stop here. Next time we will talk about the existence and the uniqueness of parallel transport. Thank you for your attention.